This is AQA A-Level Chemistry. We are looking at the topic of bonding from year 12, and this is video 4 in this series. In this particular video, we're going to take a look at the introduction to electronegativity. So that will be the principles of electronegativity, the definition of electronegativity, trends, and what impact that will have on some covalent compounds. So in the first instance, I want you to read through this, have a go at the questions, and then we'll see how we do. So the first thing to look at here is the definition. Now you've got to know this to remember it. You've got to be able to write it down in an exam. But that will be worth 1 or 2 marks. Far more importantly, you have to understand this definition and be able to apply it, because that's going to give you access to many, many more marks within your exam. So electronegativity is the tendency of an atom to attract electrons towards itself in a covalent bond. So that limits it to covalent compounds. And we've got to then think about what will attract those electrons in the covalent bond, which will be in the outer principal energy level of the element, and what might actually push it away. See what you can do. Well, if we think about the electrons being negative, they're going to be attracted to positive. So the attraction is the nucleus. That's the pull. We have got those electrons in the covalent bond and the nucleus is pulling them towards itself. But we've also got inner principal energy levels. And we've got all of those electrons that are going to be repelling the outermost electrons. So we've got both of these factors to consider. With that in mind, have a think about this question. What do you think will be the trend in electronegativity going across a period? It's important that you remember that there is an increase in electronegativity across a period. But you also need to be able to explain why. And we can dip into our knowledge from other areas that have already been covered in year 12, specifically in periodicity and the atomic structure topic. There is an increased nuclear charge as you go across the period. Each element has 1 more proton. That's 1 more positive charge attracting the outer electrons and therefore attracting the electrons in the covalent bond. But as you go across the period, there's also no increase in shielding. We've got the same number of inner principal energy levels that are going to be repelling the electrons in a covalent bond. So you put both of those things together and you can see that that atom, as you go across the period, is going to have a better pull on the electrons in the covalent bond. So what about as we go down a group? Well, as we go down a group, you will see a decrease in electronegativity. And again, let's think about why. We can think about similar ideas to why reactivity changes. And you've talked about that at GCSE. Well, in terms of electronegativity, each element has got 1 more principal energy level. So if we go down fluorine, chlorine, bromine, iodine, we're adding a principal energy level each time. That means that the outer electrons, and therefore the electrons in the covalent bond, are further from the nucleus. If they're further from the nucleus, they're less attracted. But there's also another impact, because you've got an extra principal energy level of electrons that can shield those outermost electrons and repel them and push them away. So you've got the outermost electrons, the electrons in the covalent bond, subject to more shielding. So we've got some really clear key reasons why electronegativity will go down. So let's have a think about this question. Which is the most electronegative element on the periodic table? And why do you think that's the case? There is a very good possibility, if you're doing this for the first time, based on the information that we've had, that you have said helium. However, that would be incorrect. If you did think that, have another think. The correct answer is fluorine. And actually what you can do is draw an arrow onto this periodic table to illustrate that fluorine is the most electronegative element. And you can see the arrow here going upwards towards fluorine. So electronegativity increases up a group and increases across a period. But we haven't yet explained why it's not helium. Well, it comes back to the definition, and it comes back to understanding that definition of electronegativity. Because it very clearly tells us that electronegativity is the power of an atom to attract electron density towards itself in a covalent bond. Now, helium does not form covalent bonds. It has outer electrons, but it doesn't fit the criteria, so it cannot have an electronegativity value. Okay, we're going to go on and start to think about polarity, what impact a difference in electronegativity has on a molecule. And I'm going to use the analogy of a tug of war. And in each of these 5 examples, I want you to imagine a tug of war, which is unlike a tug of war with real people, because this one has a very definite winner, loser, or draw. There's no technique here. It's purely the most electronegative will have a better pull on the electrons. So in a tug of war, you have a ribbon that hangs down in the middle, and the winner is the team that pulls that ribbon towards itself and pulls it beyond a certain point. Now, in each of the cases that we have here, that ribbon will start exactly in the middle between the 2 atoms. Based on what we've said about electronegativity, where do you think those electrons will lie? Where will the ribbon move to once the bond is formed? Have a think and then we'll review. Well, if we take the first example, hydrogen and hydrogen, we have got a dead heat. It's a draw. Both of those hydrogens are equally electronegative, so they're going to have an equal pull on the electrons. So the electrons will sit exactly in the middle. But if I take a look at hydrogen and chlorine, chlorine is a more electronegative element. That means it has a greater attraction to the electrons in the covalent bond. It will pull them closer. So the ribbon moves to the right. Now, if I take the example below, I've got H and F, hydrogen fluoride. Fluorine is the most electronegative element. So that's going to have a much greater pull on the electrons in the covalent bond. So that's going to pull the electrons closer. And you can see I've drawn them much closer to F than I drew them to Cl in the previous example. On the next one, we've got an OH bond. Once again, we've got oxygen, which is more electronegative than hydrogen. So the oxygen is going to pull them closer. It's not as electronegative as fluorine, so I've not pulled it as close. And finally, I go to ClCl, a chlorine bond, a diatomic molecule. They're equally electronegative, so the ribbon will sit in the middle. The electrons will sit in the middle. So what does that mean in terms of charges? Because we've spoken about ionic compounds before having positive and negative ions. But have a think about the questions on here and see what you can do in terms of partial charges. Now, once again, if we take a look at each example, the hydrogen, if neither of the hydrogens has a greater pull on the electrons, and the electrons sit exactly in the middle, those electrons have no influence particularly on one hydrogen over the other. So there are no charges. There is no positive, there is no negative. If I move on to the next example, hydrogen and chlorine, you can see that chlorine has pulled the electrons closer. That means that it's got more of a share of those electrons. Electrons are negative, so that's going to make the chlorine not fully negative, not a minus charge, but it's going to be partially negative. And as it says on the screen, that means we have a delta negative. Now, if this is delta negative because it's slightly more electron rich, that leaves the hydrogen as delta positive, slightly electron deficient. And if I go through the remaining examples, I have got my fluorine with a much greater pull on the electrons, but it's still not fully negative. This time the fluorine is delta negative, the hydrogen is delta positive. And on the next one, the oxygen is delta negative, the hydrogen is delta positive. The electrons are closer to O, so the O is delta negative. And the final example, we've got that dead heat once again. Neither of the chlorines have a greater pull, so we have no permanent partial charges. That brings us to the end of this video. Thank you for listening. Goodbye.